Precalculus 8.2 over the Law of Cosines. So here's our next video for Chapter 8. Chapter 8 covers covers some applications of trigonometry, namely in the area of vectors. And then we're going to go into, after vectors, it's going to be a vector treatment of the complex plane. And then after that, it goes over polar coordinates. So this little collection of topics almost seems unrelated, even though they are related to each other. It seems like a very strange way to group these things together, but that's just the decision of the authors of this book that we're using. So 8.2 Law of Cosines. So we begin with Law of Cosines, and like I had said in a previous video, this is one of the topics you've already seen in a pre-AP geometry setting. Now, if you're coming to me from a non-pre-AP geometry class, then you probably didn't see this section. So normally CP, we have to teach a little slower. And not a lot slower, but normally what that means is there are certain sections that are not what we deem essential, and we skip on those. This is probably one of those sections. So if you were in a CP class, it's likely that you didn't see it, but in a pre-AP class, you should have seen it. It's very, very important. So Law of Cosines, very much like the Law of Sines, this is some sort of identity that is true for triangles, not just right triangles, but oblique triangles, which is what we were calling them earlier. So also for oblique triangles. And it's going to have some sort of a trigonometric expression. And in this case, we're expecting sines in there. Or sorry, not sines, cosines in there. So I'll go ahead and give what that formula is. They give it here somewhere, and they give it in 3 different versions. So we have a triangle A, B, and C. And normally the way that they will orient these triangles, or the way that they label these triangles, if you call this triangle A, B, C, then you must say that this is little a, opposite of big A, this is little b here, and this is little c. So you have to make sure that little a and big A are opposites of each other, and so on. So same relationship, and if that's the case, these 3 relationships hold. So in my opinion, they're wasting space. You only need to know one of these, because it's the same geometric pattern. So it's a single geometric pattern. The pattern is one of these sides squared is equal to the sum of the square of the other 2 sides minus 2 times the product of those other 2 side measures times the cosine of the opposite angle. So that's kind of hard to follow at first, so hopefully I didn't throw you off too much, but it's that pattern for all 3. So it's always the opposite side squared is equal to the sum of the squares of the other 2 sides minus 2 times the product of those 2 side measures times the cosine of the opposite angle. So we'll see that in a little bit. And you'll get it. After a while, when we set these things up, you're only going to need one of these, by the way, and I normally use this one. So this is the 3rd version of it, and I'm going to go ahead and omit these other 2, because those other 2 fit the same geometrical pattern. It just depends where you're starting. So if you started with A, like I said earlier, then this is the formula you're going to get: b squared plus c squared minus 2bc cosine A. If you take A as your point of view, so basically it's a point of view that's shifting. So you can take A as your point of view, you could take B as your point of view, in which case the opposite, or the other 2 sides are A and C. You take A and C and multiply them, and then cosine of the opposite of little b. So you kind of see that pattern here. So it's one side, and then it's the opposite angle. It's B, and then opposite of B is big B. It's C here, and then it's big C, which is opposite of little c. And it's in here, it's the other 2 sides. If this one's A, then these are B and C, B and C. If this one's B, then this is A and C, and then A and C again. If this one's C, then this is A and B, A and B. So it's a pattern that you can memorize after seeing these problems, not for too much. So it's a very easy pattern to memorize. So that's why I'm saying it's the same exact pattern all throughout for all 3. You only need to memorize one of these things, and then you could just label it differently, so that way one of them is C, one of them's A, one of them's B. So we only memorize one. So there's only one I'm going to memorize, and it's going to be the 3rd one. Let's prove it. So I'm going to want to prove it, and I think they give a outline for the proof here again, and just like I did for the previous one, I'm going to do my own proof over on the side. So the theorem to prove. And I don't want to be too elaborate in the statement of the theorem, but we'll try to be as elaborate as we need to be. For triangle ABC, labeled this way, So using the usual convention, if we're using big A, big B, big C to correspond to angle measurements, then we're using little a, little b, little c for the opposites of the respective letters. So for triangle A, B, and C, c squared is equal to a squared plus b squared minus 2ab cosine big C. We're proving this. So we'll prove this in pieces. So we'll start off with any triangle, and this is true for any type of triangle, not just oblique triangles. It's also true for right triangles. But if we have a right triangle, and we're letting big C equal to the 90-degree angle, cosine of 90 is 0. So cosine of 90 is 0. This whole thing goes away, and we're left with c squared is equal to a squared plus b squared, which is the Pythagorean theorem. So we're not going to actually consider the right triangle case, because the right triangle case is trivially true. So it's obviously true if we let c equal to the 90-degree angle. So this is actually an extension of the Pythagorean theorem. So this is an extension of Pythagoras' theorem. And Pythagorean theorem is just one case of this more generalized property of triangles. So that's actually kind of cool. But anyway, so we'll start off with a triangle, and it could be acute or it could be obtuse. And that's not really going to matter if it's acute or if it's obtuse. Let me draw an obtuse one. So something like this. That's kind of bad, but whatever. I'll leave it that way. Or not, I'll try to fix it. So A, B, and I'm going to call this one out here C. We normally let the bigger angle be C, and it doesn't really matter. I could let that be A, or I could let that be B. Doesn't matter at all. So if that's the case, this is little a, this is little b, and the whole way through is little c, but I'm going to go ahead and leave some space in between here, that is, for some extra work. And we'll see why in just a bit. So how do I calculate, or how do I show that c squared is equal to a squared plus b squared minus 2ab times cosine c? So we're going to do this in pieces. So what's the first piece? The very, very first piece, we're gonna mess with this just a little bit. So the first part, so I'm gonna call this lemma number one, and this is a fancy mathematical term. That's not a mathematical term, it's a logical term. I'm not quite sure where the term originated. It's more than likely originated out of mathematics, or originated outside of the realm of mathematics and brought into mathematics by somebody who started using it. So I'm not sure who did. Probably something I should be looking up. But the word lemma in mathematics is used as the stating of a smaller problem that's going to in turn be used to solve this bigger problem. So if we have very complex theorems, and in mathematics, you can take an entire book, like a very, very thick book, just to outline a proof for one particular theorem. So there are theorems out there that are that big. So in that case, you would write lemmas as entire chapters. So to set up the proof for the big theorem. So, or sometimes theorems are very, very tiny and their proofs are extremely tiny. So there's actually videos on YouTube that you can look up. Usually Numberphile is a good one to look up. But they have a collection a lot of the times of like the world's smallest proofs. And some of those are pretty cool. But it depends. If you have a complicated theorem that is done in several steps, you take a lemma per step. So this is just the first step in several steps. So we'll start off with an expression for cosine of c. Cosine of c is going to equal to h squared minus xy divided by ab. So cosine c is going to equal to h squared minus xy divided by ab. And what's h? What's xy? And we know what AB are. So h, hopefully you guessed it, h is the altitude of the triangle, and that's going to stem out from c. Altitude must be drawn, so that way it's a segment from c. In this case, it's going to be c. A segment from that vertex that intersects the opposite side at a 90-degree angle. So that's an altitude. H, obviously, is going to be the length of the segment. Okay, what are x and y? That's why I left space here. X and y are going to split up this triangle, or the sides, or this particular side, into two pieces. So that's because of the altitude. So it's the two segments that result from the drawing of the altitude, which has a measure h. So those are x and y. So, whoops. Y is from here to here, x is from here to here. So there's the lemma. The lemma is equal to this. So then we'll prove this little part of the problem. That should be pretty simple. So hopefully not too bad. So how do we get this done? This is going to be done first off by calculating cosine of c, and then replacing it with an identity that's appropriate, and then using the pieces of the identity to simplify the expression down to the one that we have here. And most likely it's going to come from trig ratios from right triangles. So that altitude was drawn for a purpose, because what it does is it splits that triangle into two right triangles, and that could be done for any oblique triangle, whether it's obtuse or it's acute. So the other thing that we want to make sure to keep note of, let's call this, and let's keep track of the angle that this is for. We can call this one theta, and this other one here, we can call it phi. Since we're used to using Greek symbols anyway, so theta and phi, we've used those before in previous proofs. So we start off with cosine of c. And cosine of c is equal to, well, first off, c is split up into two pieces, theta and phi. So in place of c, I could probably write theta plus phi. And you probably already know what it is we're trying to set up here. So if I have cosine of theta plus phi, we just finished an entire chapter on trigonometric identities. There's an identity for this. This is a sum of two angles. So if we're taking the cosine of the sum of two angles, we're going to apply a cosine sum identity, which I believe there's only one. And if you remember, cosine, 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 sine, sine, sine. So that's cosine already. Cosine of the first, cosine of the second. First sine is a sine change. Sine of the first angle, sine of the second angle. So cosine of c is equal to cosine theta, cosine phi, minus sine theta, sine phi. So that's going to be the majority of the problem. The rest is just simplifying this expression. So then we go piece by piece, cosine theta. What's cosine of theta? Cosine of theta is a trig ratio based off of this angle theta. Cosine is adjacent over the hypotenuse. So the adjacent over the hypotenuse, in this case it's h over b, and hopefully that's obvious. Cosine of phi is the adjacent over the hypotenuse for this right triangle. So in this case, h over a, and we're multiplying both of those expressions. So eventually it's going to end up being h squared over b times a. I could just call that ab if I wanted to be specific about, or if I wanted to be careful with the alphabetical order of those things. Minus, so then we got to do this all over again for theta and phi, but in this case we're changing the trig ratio, or the trig function. So now we're talking about the sine of theta and phi. So sine of theta on the left triangle, we're talking about the opposite of theta divided by the hypotenuse. Opposite in this case is x, hypotenuse is b. Now if you do this for sine of phi, it's y over a. So in this case we have xy, so minus x times y over b times a, or a times b. And we're almost done. So if you compare that to what we're supposed to prove, we're already there. H squared minus xy over ab, what's the difference? The only difference is I can combine both of these fractions into one fraction with the same denominator, since they have the same denominator. They're already common denominators. And that's it for this particular lemma. So that's the first piece of the puzzle. So there's a couple of things I'm going to go ahead and do. If that's the case, it must be, well, first off, cosine c is equal to h squared minus xy over ab. There's a couple of things I could do with this. I'm going to go ahead and multiply both sides by ab, and there's another reason for it. What I'm doing is I'm kind of cheating. I'm looking at the final expression that I'm supposed to prove. And the final expression has an ab cosine c in it. So you see that ab cosine c here? There's actually a 2 in front of it also. So if you compare that over here to what we have down here, cosine c is equal to h squared minus xy over ab. There's an ab on the bottom, which I could move over with the cosine. So I'm going to multiply both sides by ab. So ab cosine c is equal to h squared minus xy. So h squared minus xy. I'm going to multiply both of those by 2 just because I feel like it. Or not just because I feel like it, but because the formula up over here has a 2 in front of it. And maybe I should multiply by a negative 2 because that has a minus 2ab cosine c. So then negative 2ab cosine c is equal to, and you could switch it, that's going to be positive 2xy minus 2h squared, and I forgot the 2, 2h squared, and hopefully that's obvious. If you distribute a negative 2 into both of those, h squared and then negative xy, that becomes a negative 2h squared, and that becomes a positive 2xy, which I'm just writing the positive one first, and the negative one second. So that's the first major implication of the lemma that we just proved. So normally whenever we see a direct implication of something that was already proven, we call that a corollary in mathematics. So a corollary is a statement that follows directly from something that was just proven. So it's basically like a logical consequence of what we just proved. It's a direct consequence of what we just proved. So the next piece of this puzzle, I might want to just go ahead and go for it. So yeah, we're going to go ahead and go for it. So what do I mean by that? C squared is equal to a squared plus b squared minus 2ab cosine c. So I'm going to try, let's see, what's something we could do here? C squared. And here's what I mean by just going for it. What is c squared? C squared is x plus y, quantity squared. Why? Because c is x plus y. All right, so x and y added together will give you the value c. And this is equal to x squared plus 2xy plus y squared. That's a perfect square trinomial, a formula that you should be familiar with. So it's a factorization scheme and a multiplication scheme for polynomials that we should be familiar with. So c squared is equal to x squared plus 2xy plus y squared. So that I'm getting based off of this idea. Okay, so I'm a long ways off. I'm supposed to show that c squared is equal to a squared plus b squared minus 2ab cosine c. But so far I have c squared is equal to x squared plus 2xy plus y squared. So I still have a little bit to go. So let's talk about the quantities x squared and y squared. So the quantities x squared, y squared, which I might want to separate those, x squared and y squared, from this 2xy quantity here, which I think I like that already, because do you see this 2xy matches this 2xy that's in here. So I might want to go ahead and take this one a step further and see what I can do with that. So 2xy, if I solve for that quantity, it is equal to 2h squared minus 2ab cosine c. And what did I do there? What I did was I added 2h squared to both sides. So this I like. So that I'm going to replace in here. X squared, y squared, and that's going to be plus 2 h squared minus 2ab cosine c. So this is what c squared is currently equal to if you follow. And how does that compare to what I'm supposed to get? C squared is a squared plus b squared minus 2ab cosine c. So for some reason, this is supposed to be a squared plus b squared. So we'll see. So then I got to go back to this triangle for ideas. I want an a squared and b squared from an x squared and a y squared and an h squared. So there's a bunch of squares of legs of triangles, specifically right triangles. We want to think of this as two right triangles still, not one big triangle. So the key is to think of it as the key is to think of it as two right triangles. So if that's the case, let's talk about this right triangle here with side lengths x, b, and h. Is there a formula that I could use that has squares of those quantities and relates them to each other? The answer is yes. It's a right triangle. Pythagorean Theorem relates the squares of the legs to the square of the hypotenuse. A squared plus b squared is equal to c squared. In this case, x squared plus h squared equals to b squared. And I'm going to go ahead and write that on the side. x squared plus h squared is equal to b squared. Now what about this triangle here? This triangle contains side lengths h, y, and a. So y squared plus h squared is equal to a squared, since a is the hypotenuse. So y squared plus h squared is equal to a squared. Now, I'm supposed to get an a squared plus b squared, and that's what's missing here. And I can take these two and I can add them. And if I add these two, a squared plus b squared is equal to, well, if I add these two, x squared has nothing to combine with, same thing with y squared. There's two h squareds, so that's 2h squared. So let's see. Let's take this and compare it to what we currently have in this formula. Actually, it shows up here. X squared plus y squared plus 2h squared shows up exactly the way we want it. And I think we're done, because that c squared is equal to, well, those three together make a squared plus b squared. And then we have the minus 2ab cosine c, which we gathered from the previous lemma. And I think we're done. That's the proof. So on an oblique triangle, c squared is equal to a squared plus b squared minus 2ab cosine c. That's kind of a long proof. And it comes from splitting up one big triangle into two right triangles. And this could work if you're working with an obtuse or an acute. And in this case, we went from obtuse, and you can go to an acute angle by making that a smaller angle, smaller than 90 degrees. So there's our law of cosines. So that'll be the first half of this particular lesson. Second half, we'll use it in a couple of examples, and then we're going to go ahead and stop. So I'm only going to go over the first 3 examples. I don't know how many examples there are total. Let me look at them. So if you're reading this out of your textbook, there's going to be a total of, and it stops there, 5 examples. We're only going to go over the first 3. There's only 5? Yeah, there's only 5. Okay. So yeah, we'll just go over the first 3. So for example number 1, maybe just the first and the third, because this one's a side angle side. This one's a side angle side also. I might want to go over them anyway if there's something different between them. So 2 boats leave a harbor at the same time, traveling on courses that make an angle of 82 degrees 20 minutes. So they're gonna be jerks and pull that stuff back out. So the degrees, minutes, seconds system. So that's not too bad, because 20 minutes isn't too bad to convert back to decimal degrees. So the problem is, though, is that if they gave this to you in degrees, minutes, seconds, your other answers are supposed to be reported in degrees, minutes, seconds. So 82 degrees, 20 minutes. So 2 boats leave harbor at the same time, and they make that angle. When the slower boat has traveled, so I'm going to make that here. So they were initially in the same area, same position. One leaves this direction. The other one leaves maybe this direction. And the angle between it looks like a 90-degree angle. Let's make this a little bit smaller. 82 degrees, 20 minutes. So one of them's faster than the other. When the slower boat has traveled 62.5 kilometers, let's say here. So that's 62.5 kilometers. The other one, the faster one, has traveled 79.4 kilometers. At that time, what's the exact distance between the boats, or what's the distance between them? So they want this distance. Okay, so the nice thing is I can go ahead and convert this to decimals degrees. This is 82.20 out of how many total minutes per degree? If you remember, 60 minutes in a degree. So this is 1/3, so 0.3333 keeps on going degrees. Normally we round that to the nearest tenth of a degree, but on my calculator, I'm going to be using as many decimals as I can. And I think that's all the information I need. I don't need to find out this angle or this angle, unless they asked me to solve the triangle. So the beautiful thing is they didn't ask me to solve a triangle. All they want me to do is to find the opposite side. So I don't need these angles. So I'm kind of happy about that because I don't want to do the trig to do that. So here's the thing. I'm going to label this as C. So the one that's opposite of the angle that's given, we're going to call it little c. And if that's the case, we can call this one little a because it's the smallest one, and this one little b. In which case this is big B, this is big A, this is big C. And then I just apply the formula. Formula is c squared is equal to a squared plus b squared, and that's supposed to be a little c, minus 2ab cosine big C. That's the formula. So it's an easy geometrical pattern. So little c squared is equal to the sum of the other two squared, a squared plus b squared, minus 2 times, you multiply them, times the cosine of the opposite angle big C. So opposite of what? Opposite of little c. So it's always a side angle side situation, or in this, or some cases it's a side side side, because you could have all three sides and they're going to want the angle in between. So in that case you would use law of cosines as well. So side 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 or side angle side is where you're able to use law of cosines, no problem. Okay, so then we'll set this up. C squared little c is unknown. That stays variable. So c squared, I don't know. A squared. So little a, 62.5 squared. Little b, 79.4 squared. Minus 2 times little a, 62.5. Little b, 79.4. And then cosine of big C, 82.3333, keeps on going, degrees. I'm going to want to move this further down. So I'll move it down here. I have the space, I think. Yeah, I do. Then I'll go ahead and put this in a calculator, which I'm not going to end up showing the calculator. So what you're going to end up doing is calculating c squared, and I'm only going to type in the stuff to the right. Or if you wanted to get it done in one shot, you can calculate, or what's it called, type in a square root first, and then inside of the square root all of the stuff to the right hand side, and you're done for C already. So I'll just show you what the square is first, and then we square root it afterwards. So 62.5 squared plus 79.4 squared minus 2 times 62.5 times 79.4 times cosine, and make sure you're in degrees. Right now I'm in degrees. So 82.333333. I'm going to give as many threes as I can. And this is going to give me 8886.52. So that doesn't make sense. That's a really, really large number. That's because it's squared. So if we square root it, so square root both sides. So square root 888652. This is roughly 94 point, and notice how they gave 3 sig figs. So I'll give 3 sig figs. 94.3, and that's in kilometers. And that's what they wanted for example number 1. So it was a direct application of the law of cosines. Only thing here is I had to take a square root both sides in order for me to solve for C. Very straightforward. It's just knowing what the formula is. Applying it, it's super easy. Where does this get tougher? They might also ask for these other angles. Right? So if they ask for those angles, what then? So if they say solve the triangle, so we already have little c, then in order for me to find one of those angles, I might want to resort to the law of sines. That's where I compare pairs of opposite sides and angles. So I would use sine of big C divided by little c equals to sine of big A over little a, and you can solve for big A. And you'd have to take an inverse trigonometric function to get that done. And I think they're going to ask us for that for example 2. So let's try that. Solve triangle ABC if B is equal to 73.5, little a is equal to 28.2 feet, and then little c is 46.7. So what I'm going to do is I'm going to draw that. What type of triangle is that? I don't really know. So they're giving me a acute angle, 73.5 degrees. Little a, which is a shorter one, this is, let's see, this is big B, by the way. Little a, 28.2 feet. Big C, or little c, sorry, 46.7 feet. I kind of don't care what type of triangle it is. We'll determine what that is in a little bit. This is A, and this is C. Okay, they want me to solve the triangle, and that means finding this side length, this angle, and this angle. I need all three of those. Which do I solve for first? So, if you wanted to use law of sines, I need to have an angle and an opposite side given, which I have none of that. So I have this side, but not its opposite angle. I have this side, but not its opposite angle. I have this angle, but not its opposite side. So I can't use law of sines in this situation. So I'd have to use law of cosines first. So we can find this one by using the formula. And the formula is, well, in this case, this is little b, right? So that's unknown, and it's little b. So how do I find little b? B squared is equal to the sum of the squares of the other two, a squared plus c squared, minus 2 times a times c, the other two, times cosine of the angle b. So the same letter from the one that's outside. And that's the formula, that's the pattern. So it's a pretty easy formula to memorize, and that you can build it just by looking at the triangle, no problem. So we fill in what we know, and what we know is, well, I don't know b. That one I don't know for sure. Little a is 28.2, and we're going to square it. Little c is 46.7, we're going to square it, minus 2. 28.2, 46.7, cosine of 73.5. Calculator. So what I'm going to do is I'm going to go ahead and find, and that's b squared, by the way. B is going to equal to the square root of all that, so I'm going to do that all in one shot if I can. So I'm typing in square root first. Make sure inside of the square root, 28.2 squared, 46.7 squared added to that, and then subtracting 2 times 28.2 times 46.7 times cosine, make sure you're in degrees, 73.5. And I'm double checking to see that if I typed this in correctly, and it looks fine. Yeah. Press enter, and I'm getting 47.2. And I'm going to restrict myself to 3 sig figs because that's the way that they have it for the sides, 3 significant digits. So B is 47.2. So then we can answer the question, what type of triangle is this? Is this an obtuse triangle or is this an acute triangle? So that's kind of a side note. Is this obtuse or is this acute? And the way that we can figure that out, there's an old formula from geometry. You take c squared and you compare it to a squared and b squared added to each other. So c squared, 46.7 squared. And actually, no, that's not c squared. You take the biggest one. So here they're violating a rule that I like to go by. The rule that I like to go by, largest side needs to be c. So it's going to be a little confusing. You take the largest side, 47.2, you square it. So 47.2 and squared, 2227.84. And then you take the other two, the smaller two, 28.2, square it, add it to the other one, 46.7, and square it. So 28.2 squared plus 46.7 squared. And we get 2976.13. If you add both of those quantities together, then you compare these two. So this one compared with this one. So then what I'm going to do from left to right, this one's smaller. So if c squared is smaller than a squared plus b squared, that's an acute triangle. So this one's acute. If they were equal, c squared is equal to a squared plus b squared, that's obviously right. If c squared was larger, then it's obtuse. So this is acute. So that's just a side note, extra little stuff there. And sometimes it's important to know what type of triangle we're dealing with. So it's nice to know that this is an acute triangle. So I'm expecting numbers that are smaller than 90. And that's going to be an issue with obtuse triangles because if you remember, inverse sine of an angle theta is always between Actually, no, not inverse sine of theta. Inverse sine of, let's say, y is always between negative pi over 2 to pi over 2. 90 degrees, negative, and positive 90 degrees. So inverse sine will only spit out acute angles for you. It's not going to deal with obtuse angles. So it's only going to give you acute angles. So what that means is, the reason why I checked, since we're working with an acute triangle, all of these are acute angles, and if I use the law of sines, I'm going to have no problem with reporting the exact answers I get using the law of sines whatsoever. Now, if this were obtuse, and one of those other two angles is larger, I might want to continue using the law of cosines. Law of cosines, the reason being, inverse cosine will report any angle between 0 and 180 degrees. That's something we learned in the previous section. So you're safer using law of cosines all the way throughout. Law of sines is the one that's a little bit trickier. But in this case, we're safe to use law of sines because it's an acute triangle. So law of sines, then, we have sine b over b. And I want to use that because those are the two that we have. And then we're going to use one where one of them is missing. Let's say a over a. So I know sine of b over b. Sine of 47.2. Oh, no. Angle 73.5 over 47.2. Supposed to equal to, I don't know the angle, sine of a, over the side length, 28.2. And in this case, it's going to be a little bit different than what we saw in the previous section, because we're not solving for a side length. Now we're solving for an angle. So I need to solve for the angle a. So I need to isolate sine a. And the way to do that, you multiply 28.2 both sides. So you get sine a equals 28.2 times sine 73.5, all divided by 47.2. And you solve for a by taking an inverse sine of all of the stuff to the right. So inverse sine of 28.2, sine of 73.5, all divided by 47.2. And I got to type all that into my calculator. Inverse sine 28.2 times sine 73.5 divided by 47.2. I'm in degrees and I'm getting 34.95. So I'm going to just round that to the nearest tenth of a degree. 3 sig figs. So 34.9. So that's what I'm getting for A. I'm going to box that. Also, I should probably box this one and not leave this one circled at all. So now I only have one last piece to figure out. Am I using a law of sines or cosines for that one? What's missing? One more side length, or one more angle. Do I have to use cosines or sines, the laws of sines or cosines? Answer is no. I could use the triangle rule, the 180 law. So if I take both of those, 73.5, and I add them, 34.9, added with the 73.5, we get 108.4. Subtract that from 180 degrees, and we get 71.6 degrees. And that's it for this particular problem. So there's two applications of trigonometric identities. One of them is the law of cosines to solve for the missing side length, and then a single application of the law of sines to find one of the other missing angles. And then we just use a simpler formula, the 180 rule, to solve for the third missing angle. And that's it for example 2. So that's the majority of what we need to know for this particular section. We're going to go ahead and go over example 3 though, because it's slightly different, where they give you 3 side lengths, no angles. Totally doable. Still using the law of cosines though. And we're going to see why. So for example 3, solve triangle ABC if A is equal to 25.4, B is equal to 42.8, and C is equal to 59.3. So here they're not going to violate the rule that I was talking about earlier. C is the biggest one. So that makes me a little happy. So what I'm going to do is I'm going to draw a obtuse I think it's because I already know that this is obtuse ahead of time. But we're going to show that it's obtuse. So this is C. This one's a smaller one, A. Actually, no, that's B. This one's A. The smallest side corresponds to the smallest opposite side. Okay, so, and I drew that probably a little too big, so I don't have any room for the work. So I'll move this over here, and I got to still make that a little bit smaller. That should be good enough. So, big C, 59.3 centimeters, or little c, sorry. Little a, 25.4, little b, 42.8, and these are centimeters. Okay, the first thing I'd have you do is check to see what type of triangle it is. Take 59.3, since it's the largest one, square it. And this is equal to, so 59.3 squared, 3516.49. Then you take the sum of the squares of the other two. 25.4 squared plus 42.8 squared. And I'm getting 2477. This one's clearly bigger. And because c squared, and this one's c squared, this one's a squared plus b squared. When c squared is larger, this is obtuse. And like I said earlier, there's a reason why that matters. In a side-side situation, it doesn't if you follow a particular rule. So the reason why that matters, sometimes you might want to use the law of sines to solve for an unknown angle. And if you're put in that position of solving for an unknown angle that happens to be obtuse, you're going to get the wrong angle when you use an inverse sign by solving the law of sines. So when you're solving when you're applying inverse signs, inverse sign on a calculator is designed to give you a negative angle between 0 and 90, or a positive angle between 0 and 90 degrees. So it will not spit out an angle that's bigger than 90. So sometimes what ends up happening is it's going to end up giving you an acute angle that's positive, but that corresponds to a completely different triangle. So how do you avoid this? For a side-side situation, you're going to use law of cosines and solve for the biggest angle first. Basically, take down the biggest guy first. So this is the strategy you want to go with. Take down the largest angle first and use law of cosines. Law of cosines is good at taking down any angle, so we'll use the law of cosines to figure out the largest angle first. So c squared then is equal to a squared plus b squared minus 2ab cosine big C. And big C is what we're going to solve for. So little c squared, 59.3 squared. Little a squared, 25.4 squared. Little b squared, 42.8 squared, minus 2 times 25.4, 42.8, cosine of c, which is a variable right now. So I don't know what c is. So then I have to solve for c. This is going to be a little tough. So we have to solve for this one. And what I do is I'd subtract these, 25.4 squared, 42.8 squared. Those are going to cancel on this side. You're going to end up getting 59.3 squared minus 25.4 squared minus 42.8 squared is equal to negative 2 times 25.4, 42.8 cosine C. So then the last thing I do is divide both of these quantities by negative 2ab, or negative 2, 25.4, 42.8. So then cosine C is then equal to 59.3 squared minus 25.4 squared minus 42.8 squared, all divided by negative 2 times both of those multiplied. And then if I want C, it's equal to the inverse cosine of all of that stuff up here. Forgot the minus 1. So inverse cosine of that big ratio. I'm already in degrees, so I'm going to try to do that in one shot. So inverse cosine. Now, on a calculator, you want to be careful. Two sets of parentheses. So first parentheses set, open and close, divided by second parentheses, open and close. Go in between the first open and close parentheses, and you're going to type in 59.3 squared minus 25.4 squared minus 42.8 squared. That's going to be divided by -2, and you're going to move this in between the other two sets of parentheses, or the other two parentheses. -2 times 25.4 times 42.8. Press enter, and if you've done this all correctly, you're supposed to get an obtuse angle. 118 point, in this case 6 if you round to the nearest tenth of a degree, which I don't know if they gave us instructions, and no they did not. So I'm going to go ahead and go with the nearest tenth of a degree. And does that coincide, or is that consistent with what I was predicting earlier? I predicted this was an obtuse angle, and because I chose little c to be opposite of the largest, or big C to be opposite of the largest side, that's going to be the biggest angle. Obtuse means the biggest angle is supposed to be an obtuse angle. And yeah, it worked out that way. So 118.6 degrees. Okay, so that's the hard part. The hard part's not over, but that was the scariest part about all of this because it was obtuse. So there was a possibility of me getting an incorrect answer if I had used the law of sines first, or if I had used the law of cosines to find one of the other two, then use the law of sines to find this one later. That's a bad strategy. The good strategy is to kill the biggest angle first using law of cosines. So go with law of cosines first on the biggest angle. That's my advice. Second step, law of sines. Sine of that angle, 118.6 degrees divided by 59.3. And then set that equal to sine A over A or sine B over B, whichever you prefer. So I'm going to go with sine A over A first. Sine A, that one's unknown. Little a is known, 25.4. Cross multiply, you're going to get sine, actually no, you can just kill this in one shot. A is equal inverse sine of 25.4 sine of 118.6 divided by 59.3. And if you do this on your calculator, we're working in degrees, 22.1 roughly, rounded to the nearest tenth of a degree. So there's the next bit of information. I think I should box this one too. This one's big C. Last bit of information, B is equal to 180 degrees minus the sum of those two, 118.6, and then minus, 21.1, if I just write it all together as one big sum or difference. And if you do this correctly, 39.3 degrees. This is the value for B, big B. And this one is example 3. That's an example of a side, side situation. And this is essentially what it is I want to go over for 8.2 for the law of cosines, just how to apply it and solve triangles. So pretty simple if you practice.